Hello, so there are two homework assignments, one from Unit 2, Module 2b, and one from Unit 2, Module 3a. Several students came into office hours with questions regarding the homework and the quiz, and I captured those and we will discuss them here. Okay, so this question is about the connection between radii, ionization energy, and the column effect about different elements in the same column. Alright, so let's take a look. So helium and neon are in the noble gas column. And if we're looking at size, we usually use the shell model here to discuss general size. So helium is smaller than neon. Neon has one extra shell, the second shell. So helium is smaller, neon is bigger. That means the proton-electron distance is farther apart for neon. So that means that the first two options have to be wrong. I mean, helium cannot be bigger if it has one shell less. So now the choice is, okay, we know neon is bigger, but what about the ionization energy? Okay, so the way size relates to that is, as we discussed in class, you could think of the farther the proton and electron are, the lower the amount of energy required to remove it. So since helium's electron is much closer to the nucleus, it takes much more energy to remove that electron, right? To get it from the orbital energy up to zero, right? Because remember, the orbital energy is negative, it's attractive. And so here we see that this requires more energy, the helium does, than neon. Neon has an outer shell, the electron's farther away, it's much closer to zero, and it requires less energy to promote it, and in that case the first ionization energy for helium is greater, and we would pick A. Okay, in this question we're asked which +1 ion would have this photoelectron spectrum. So let's analyze that. We had a lot of questions in office hours regarding the photoelectron spectrum. So what are we seeing? We're seeing electrons that are being ejected from different parts of the atom. So we have the inner orbit electrons, the 1s2. Then in the second shell we have 2s2, 2p6. And then in the third shell we have 3s2, 3p6. So this would be the electron configuration. These levels are separated by big gaps in energy that are called shells. The outer shells have the lowest ionization energy. The inner shells have the highest ionization energy. Okay, so shell 1, shell 2, and shell 3. Right, so what we're being asked is which atom or ion, or which atom would have a +1 ion. Okay. So what we're going to do is first we're going to add up the total number of electrons here. That's 18 electrons are being shown. So we can use the formula that the number of the total charge is equal to the number of protons minus the number of electrons. And when we do that, what we see is that we can solve for the number of protons as 19. When we look on the periodic table, element 19 is potassium, which is represented by the atomic symbol K. And so the answer would be K+. Okay, in this problem, this is from the homework, we're being asked to rank radii, and this is going to be done using column effects or different shells. And so one thing we're going to notice is that as we go, so this is the first column, but as we go down the column, right, starting with lithium, sodium, potassium, rubidium, and cesium, that we're adding shells. We know we're adding shells because we're going down rows, so each row represents a new shell. And when we do that, this is the clearest increase in size with atoms because we're adding another layer, the electrons are farther out, and they get bigger. So I try to use size representation here with cesium kind of being the biggest. So as you go down a column, the outer shells get farther away from the nucleus and they are bigger. So when we rank these, outer shells, 6. So lithium is the smallest, then sodium, then potassium, then rubidium, and then cesium. So this is the clearest increase in size on the periodic table, going down a column. So each shell increases the size of the atom. Now when you go within a shell, right, when you're within a shell, where we're talking about lithium versus beryllium, right? So this is going across, then what we see is a decrease, right? A decrease in size as we add more protons into the same shell. So if we're going across a row, there's a contraction, everything gets smaller. And so beryllium is smaller than lithium because we're adding more protons into the same shell, leading to a smaller size. So that's much less straightforward than going down a column, but it is the other trend that we have in the periodic table for size. That as you go across lithium, beryllium, boron, as we do that, we increase in size going this direction. That boron is smaller because it has more protons pulling in the electrons within the second shell. And so this question is in the quiz and also in the homework, and it's about picking the right Lewis structure for HPO. So initially when we look at this, it might look pretty complicated, and so what we need to do is isolate the important aspects of the problem to make it clearer. How do we pick the right answer? Right, so the first thing we're going to note is that hydrogen is going to form one bond, 2 electrons. That's its closed shell. That's helium, right? So remember, each element will bond in a way that closes, that creates the noble gas configuration, the lowest energy configuration for an atom in its row. So helium is the noble gas in hydrogen's row, and that would be with 2 electrons. Phosphorus is going to form 3 bonds, and it will have 1 lone pair. And oxygen will form 2 bonds, and we'll have 2 lone pairs. Now remember, this is due to the electron configurations that we discussed in class, that to find the number of bonds that are going to be produced, you will sum up the total number of outer shell electrons. So for phosphorus, that's 5, 2s2, 3s2, 3p3, and oxygen, 2s2, 2p4. Okay, so now we have, so the outer core of phosphorus is 3s2, 3p3, so that number of electrons plus the number of bonds has to equal 8. So that's 5 plus number of bonds equals 8. And that's where we get number of bonds 3. If we do that with oxygen, this is 2s2, 2p4 plus number of bonds equals 8. So that means we'd have 6 plus number of bonds. Number of bonds is 2. So that's where we get, that's for oxygen, that's for phosphorus and nitrogen, right? They're the same. And so now when we look at these molecules, representations of the Lewis structure, we're going to do it through that lens, right? We want to say, make sure phosphorus has 3 bonds and a lone pair, oxygen has 2 bonds and 2 lone pairs. So let's start looking at these options. So hydrogen clearly has 1 bond, that's good. It has 1 bond in all 4 options. But when we look at phosphorus here, phosphorus has 4 bonds and 1 lone pair. Oxygen has 3 bonds and 1 lone pair. So that's definitely out of our analysis. Let's look at phosphorus here has 2 bonds, 1 lone pair. Oxygen has 1 bond and 3 lone pair. That's also out of our analysis. We look at option C, 1 bond for hydrogen, 3 bonds for phosphorus, 1 lone pair, 2 bonds for oxygen, 2 lone pair. That's exactly how we predicted the bonding to be. And then if we look at D, 1 bond for hydrogen, 3 bonds for phosphorus, but then there's 2 lone pairs, and then oxygen has 2 bonds and 2 lone pairs. So that would make D incorrect because of the additional lone pair there for phosphorus. That would give us option C. We can also count the number of electrons around the central atom, and that will also, we have to complete the octet, the 8 electrons. So all of the structures that have either 10 electrons or 6 electrons around a central atom can be discarded. But to obtain the number of bonds, we can either use the valency model, where you just count columns from the noble gas to count them, or you can use this justification to count the number of bonds plus the outer shell total electrons have to equal 8, and you can solve for it. Which atom has the following electron configuration in its ground state? Right, so let's take a look at krypton, 5s2, 4d6. Right, so when we look at that, let's see, how are we going to analyze that? Well, what we're going to do is go to the 5th row, and the first, right, so we see the first 2 electrons in 5s2 is rubidium and strontium. And then we go over to the Ds, right, there's a total of 10 there. And we look at yttrium, we'll have 1, zirconium, niobium, molybdenum, technetium, 4d5. And when we get to 4d6, it is ruthenium. So we would pick ruthenium here as the element that has 5s2, 4d6 as its ground state electron configuration. Right. Right, we did that one. Okay, so this is a question from the quiz. And so what we're going to do is we're told we're given 2 atoms, right? And they have this ns2np3, which looks a little strange initially with these N's. So let's kind of decode that. So what we're going to do is we're going to look at the first couple N's just to sort of make sense of it. So we have a noble gas, so Ng stands for noble gas. And so if we start with the first noble gas, helium core, so helium core, and when N equals 2, it looks like that, right? And that's our friend nitrogen. Then we have neon, 3s2, 3p3, when N equals 3. We have phosphorus, and on and on. And the other, in Y, that was for X, and for Y, when we use this, so starting with helium, N equals 2, we get fluorine. And then we do neon with N equals 3, we get chlorine. And so now this is much more straightforward. It was really asking what is the molecular what do we expect the molecular formula, the molecular compound to be when nitrogen combines with fluorine. All right, to do that, we look at nitrogen's bonding capacity. How many bonds? Well, we just discussed that with phosphorus. So, but if we use the periodic table, we see that nitrogen forms 3 bonds. You could also make the argument like we did with the electron configuration. Outer shell electrons 5 plus bonds equals 8. So this is also 3. So either way, multiple ways to do this. So nitrogen is going to have 3 bonds and 1 lone pair. So we could just start with the 5 electrons around nitrogen. Now each fluorine is going to bring 1 electron. It has 7, right? 2s2, 2p5. And the 7th electron is going to be delocalized to make a bond with nitrogen. And we're going to do that 3 times. 1 fluorine cannot do all 3. You need 3 different fluorines to do it, since the bonding capacity of fluorine is 1. Right, so X is nitrogen, Y is fluorine, and so we'd expect the formula to be like this, NF3, right? So NF3, nitrogen has the lone pair, a total of 8 electrons around it. Each fluorine has 8 electrons around it. That should be a good Lewis structure. Okay, so there's another way to ask the question. We are given 2 atoms, A and B. They want to know what formula of the molecules would likely be formed. Okay, so we're going to do, get the electron. We want to identify what A is. So 1s2, 2s2, 2p6, 3s2, 3p2. Okay. So, neon 3s2, 3p2, okay, that's going to be silicon, right? So this is silicon, and silicon is right below carbon. So you know what's going to happen with silicon. It's going to form 4 bonds, just like carbon. There's only 4 electrons in the outer shell. It needs to delocalize that 4 to obtain a total of 8. So what is it being bonded to? So 1s2, 2p4. So if we look at that, helium core, 2s2, 2p4, well, that's oxygen. So silicon's bonding capacity is 4. Oxygen's bonding capacity is 2. So what we could do is, clearly 1 oxygen is not going to be able to do it. So we talked about the structure of CO2. Looks like this, 2 double bonds. By doing that, we get 8 electrons around the central atom, either silicon or carbon, and the 2 lone pairs plus the 2 bonds for each oxygen contribute to 8. So we would make something that looks like this. Whoops. AB2 or B double bond A double bond B. And I really suggest that you convert the PES spectrum into an element. It makes it so much easier to construct the molecule, because we usually have a lot of familiarity with the column chemistry, and that helps us build the molecule. Right, so how many double bonds are present in C3H4O2? So this is coming from the homework. And so what we want to do, but you're given a hint. You say assume all atoms satisfy their bonding patterns, and that carbon atoms are bonded in a linear chain. Okay, so what's that mean? Well, that means we got to take the carbon atoms and put them in a linear chain like this. And we have to attach 2 oxygen atoms to it. Now, you could put both of them on the same carbon, but I started with oxygen on different carbons. And now, well, to each carbon needs 4 bonds. And so if one carbon doesn't have an oxygen, well, it's going to need hydrogen atoms. So we've taken the first 3 of the hydrogen atoms and put it onto the carbon that doesn't have an oxygen. And we only have 1 hydrogen atom left. And so for the remaining, so this is where the double bonds are going to be really important, because we're going to want to complete the 8 electrons around oxygen and carbon, the remaining carbons, 1 and 2, call this 1 and 2, to be able to have a valid Lewis structure. Okay, so we could put the hydrogen here, but if we do that, then this oxygen here would not have a full octet. So can't put it there, so we're going to remove it. Next thing we do, okay, well, the most straightforward aspect of this is just put a double bond attached to that oxygen. Now the carbon 1 has 4 electrons, and by putting the lone pairs in for oxygen, we put 2 double bonds in here, and by doing that we have and so we're missing 1 hydrogen, so we can put that hydrogen here. And if we do that, we have each carbon has 4 bonds, each oxygen has 2 bonds, each hydrogen has 1 bond. We have the correct formula, so the answer is 2. Put our lone pairs here. 2 double bonds. Now we could have drawn it a different way. You don't have to do it this way. We could say, hey, why don't we put a double bond in the carbon-carbon chain? Okay, let's try that. That would give us 2 hydrogens on the outside carbon, the one that doesn't have an oxygen to it. We could now put an OH there. So now the central carbon already has 4 bonds. We could put a double bond on that O. And now to complete the bonding patterns here, we would now have 4 hydrogens, right? So we have the same formula, a molecule with very different properties than the one that we drew initially, but still it needs 2 double bonds. So any way that you draw this molecule, you're going to need 2 double bonds to have the correct formula and to have the correct bonding capacity. Okay, so how many double bonds are in the molecule of NaCl? Right, so let's take a look at, so nitrogen is 3 bonds, oxygen is 2 bonds, and chlorine is 1 bond. Well, we get that from the periodic table. Okay, so first we put the atom with the largest bonding capacity. And so remember, there's 2 ways nitrogen can be a central atom. It can form 3 single bonds, or it can form a double bond and a single bond. Okay, so let's take a look at that method. So the only atom it can form a double bond with in this molecule is with oxygen. And oxygen, so now what we've done is oxygen now has its 2 bonds. We put the 2 lone pairs there, and now we're going to form the single bond with chlorine. So we're going to look at the Lewis structure. It would look like this. If we do that, chlorine has 8 electrons around it, nitrogen has 8 electrons around it, and oxygen has 8 electrons around it, and we have met the common bonding pattern of nitrogen having 3 bonds, oxygen having 2 bonds, and chlorine having 1. So the answer here is that there's 1 double bond. Right, so this question is about the correct electron energy diagram for sodium. Right, so sodium has 11 electrons and 11 protons. Remember, the 11 protons are down here, right? So down here is where the nucleus is. At 0 is the edge, right? The 0 is where now the electrons would be lost at any energy above 0. So let's take a look at some of these orbits here. We know sodium is 1s2, 2s2, 2p6, 3s1. Alright, so we look at A is 1s2, 2s2, 2p6, 3s1. So A is looking good. What about B? 1s2, 2p8, and then 3s2, so B is definitely wrong. C is 1s1, 2s2, 2p6, 3s2. So it looks like an electron has been promoted from the 1s up to the 3s. So C is definitely not the ground state. And then we look at D, 1s2, 2p8, 3s1. So we can, the 2p8 is definitely wrong. So we would consider C to be an excited state of sodium. Why? Because it has the right electron configuration. It's just the electrons are not shown in the lowest energy state. Meaning we could imagine putting in some energy and promoting an electron from the 1s up to the 3s. That can happen. But it's definitely not the ground state. So we would pick A. A represents all the electrons in the lowest energy possible. Right, so we had many questions on this one in office hours, so I want to go through it. Let's take a look. So what we're really looking at is the choice between two atoms here. What are the atoms? Fluorine, the ground state, 1s2, 2s2, 2p5. And so in A, what they're saying is, in A, we're promoting one of the 2p5s into the 3s outer shell. And then in the next option, we're looking at oxygen, which has a ground state of 1s2, 2s2, 2p4. What we're doing is we're promoting one of the 2p4 electrons up to 1s2, 2s2, 2p3. That's why that's why there's 3 in the p's instead of 4, because it's now been one of those electrons has been promoted to 3s1. So those are the first two states, and then we can look at C and D sort of the same way. We're starting with oxygen, and then we're promoting an electron. Right? So it's really ground state versus excited state. And then what we're taking here is 1s2, 2s2, 2p3, and we're promoting that fourth p electron up to 3p1, even farther out than 3s's. And then we do the same thing with fluorine, starting with its ground state, 1s2, 2s2, 2p5. We take that fourth electron and we put it out to the 3p1. Alright, so now with that, we can now answer the question, which of these electrons are going to be at the highest potential energy? Well, that's going to be the electrons that are farthest out, and that has to be here with the 3p1s, right? So those are going to be so remember, oxygen is larger than fluorine. Remember, that's due to the size effect. Within a shell, if you add more protons, the atom gets smaller. So that's going across a row. So oxygen has 8 protons. Fluorine has 9. So the greater the number of protons within a shell, right? Within a shell, going across a row, they get smaller. And so if you're smaller, then the ionization energies always go up because the potential energies are always lower. So in this case, what we would say is the electrons are closer to the nucleus with fluorine. The amount of energy required to promote an electron in fluorine up to the 3p1 would take more energy, would be at a higher potential energy than with oxygen. So it would take more energy for fluorine. Okay, so with that, that is a summary of all the questions I was asked during office hours regarding the 2 homework assignments. Remember, that's Unit 2, Module 2b, and Unit 2, Module 3a. Right, so both of these are due on Sunday. They have a pop quiz associated with them that's also open. And my hope is that by viewing this video, you have gained some insight into the types of questions and responses we expect from you on this homework set. All of these questions will be present on exam 3A when we return on Friday. I believe it's the 14th.